Okay guys, let's talk about Class 2. With Class 2, we discussed a number of different things. We started with a discussion on our rules about exponents. Remember last class we talked about exponents and we talked about how you can have any number raised to a certain power. And remember what that represents. That represents that base multiplied that many times. So meaning 4 to the third power, or in other words 4 cubed, means 4 multiplied 3 times, which we know to solve that we would take 4 times 4 times 4, and the answer to that would be 64. Now this class we discussed in Class 2, we talked about how when we're doing things to different exponents, we have different rules involved for those to help us to solve those a little bit quicker. On page 18, we started with expressions with zero and negative exponents. And those are just a couple of the rules with exponents, just knowing that anytime you have any base raised to the power of 0, that is simply going to equal 1, no matter what. Anytime, no matter what the base is, in that case 7 to the 0 power would be equal to 1. If I had 87 to the 0 power, that would also equal 1. Anything raised to the power of 0 always equals 1, no matter what. No matter what the number is. So when we're coming across different multiplication problems, we're going to be able to see that when we have a 0, we know that that's equivalent to 1, and we'll talk more about that here in just a second. The other rule on that page is it discusses negative exponents. A little bit kind of strange, but anytime we have a negative exponent, kind of hard to think if I have, whereas we had 4 to the negative, or I'm sorry, we had 4 to the third power a second ago, we know that that meant 4 multiplied 3 times. Well, 4 to the negative third power is a little bit different. Harder to think, how can I multiply 4 negative 3 times? Instead, an easier way to simplify this would be to just take that and kind of make it a fraction. You make that 1 over 4 to the third power. That's how we would simplify that. So when we're solving that completely, that would represent 1 over 64. So it ends up being a fraction. So that's how we would solve anything with a negative exponent. So when we're just simplifying exponents, that was us completely solving that. But whenever we're just simplifying, so if I have, say, x to the negative 7, we would simplify that and just make that 1 over x to the 7th. So you always, that's the rule that they're discussing. They put that in a little table for us on page 19. They showed you that anything to the power of 0, remember, is always equal to 1. So they show b to the 0 power is 1. So that's just kind of a rule to remember. No matter what, anything to the power of 0 will always equal 1. And another thing to remember, in that second row on that chart, they show us that b to the negative n power, so whatever that number might be, we would just simplify that as 1 over b to the nth power, the positive version of that. And they show us how that can be simplified. So they give us another example with 4 to the negative 1. They show that that's the same thing as 1 over 4 to the first power, and we know anything to the first power is just that number, so we can even just erase that, and that would simplify to 1/4. So just some things to think about as we go through different operations with our exponents, that anytime you see a negative exponent, we can simplify that as putting that into a fraction, but we just take that base and put it in the denominator, and the power just becomes positive in that case. So those are just a couple rules. We're going to look at the next page, go over to page 20 and 21, and it discusses, really on page 21, we're really going to look at that table R5 to talk about the properties of exponents. There are some other properties that we discussed this week with exponents. There's some rules to remember and ways to simplify our exponents a little bit faster. The first property that they discussed is what's called the product rule for exponents, meaning that if we have two numbers that happen to be the same base, so they show it as b to the power of m, some number, if we're multiplying it by something else with the exact same base to a different power, we can simplify that by simply just keeping the base and adding together the two different powers. So giving you guys an example with that, let me get this out of the way. So if I had, say, 4, I'm going to use 4 to the third power again, and I was multiplying it by 4 to the fifth power, that can simply be looked at as 4 to the eighth power, because we're simply just taking this 3 and this 5, and we're just adding those two together. That's how we get that exponent. A way to think about that and why that works is because it's multiplying. Remember what exponents represent. Exponents represent a multiplication problem. 4 to the third power is 4 times 4 times 4. Whereas 4 to the fifth power is 4 times 4 times 4 times 4 times 4. Sorry, I had to write that real quickly there. Now again, because we're multiplying, this just becomes, when we're multiplying these two things, all it is now is just one long multiplication problem. So here you can see, in just, looking at what we see on our screen here, 4 times 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 4. In other words, 4 to the eighth power. So that works in multiplication. It's just a faster way to do that because it just becomes one long multiplication of all the same number. And again, that would not work if they were two completely different bases. If I had, say, 4 to the third power and I was multiplying it by 2 to the third power, that wouldn't work because this is 4 times 4 times 4 and this is 2 times 2 times 2. Two completely different things going on here. So when we multiply these, it's not like we have one long multiplication problem of the same number anymore. So that product rule doesn't work if the base is not the same. Now, yes, we could simplify that particular problem by actually calculating that out. 4 times 4 times 4 is 64, and 2 times 2 times 2 is 16. Is 8. So so that's, we could definitely take 64 times 8. We get that. But right now we're just looking at simplifying and quick rules that we can take into account when we're dealing with the same base. So they show us that example for even simplification problems. So when we're taking, say, x to the fourth and I'm multiplying times x to the third, that simply just becomes x to the seventh, and that would be our answer there. We don't have to solve that all the way down. We're just simplifying. And again, that's called the product rule. So anytime you see exponents with the same base, if I gave you guys a different problem, if I gave you w times w to the fourth times w to the second, remember, keep in mind that, even though that first w doesn't have an exponent on it, that's the same thing as that power, power of 1. So really, in adding these three exponents together, we would just take 1 plus 4, which is 5. We know then plus 2 would be 7. So I'm going to write that down as w to the seventh would be our solved solution to that particular problem. And so showing you guys just another one. Let me get this out of the way here. Let's say, let's see, and even when we have numbers in front of our exponents, we can still apply this product rule. So what I mean by that is if you had, I'm going to give you a problem that's, I saw when looking at some of the homework questions, even if I had something like this, negative 5w to the fourth power, and I'm multiplying that by, say, negative w to the fourth power. And so that parentheses there just simply means to multiply those two terms right there, negative 5w to the fourth and negative w to the fourth. What we can do is we can actually separate the numbers from the exponents here. So our numbers in this problem we have are negative 5, and then over here I know it's just there's no coefficient in front of that variable, but negative there just means negative 1. Remember, if there's no number there, you can always assume to see a 1 there. So that's the same thing as saying our numbers here are negative 5 times negative 1. Remember, I'm kind of applying that distributive property here, that I'm taking that and multiplying, and at the same time 4 to the w times 4 to the w. So there's our coefficients there. We know negative 5 times negative 1, remember, same sign means positive answer. So our number to our solution is going to be 5, just positive 5. Whereas then looking at just our bases with our exponents there, w to the fourth times w to the fourth would be w to the eighth, because I'm simply just adding together their exponents. So the solution here that I'm looking for is 5w to the eighth. Don't forget that even with those coefficients in there, don't be thrown off by those. We can simply just put those together as well. So again, that's called the product rule. So the product rule means that you can just take, as long as it's the same base, you can combine those two and just simply add together those exponents. Kind of similar here in the next rule down on that property list, we're looking at the quotient rule. Well, the quotient rule says that whenever I'm taking two numbers with the same base, so they show in our chart there, so they're just using any number b raised to any power m, and if we're dividing by that exact same base with a different power, our simplifying here means that all I can do is, or what an easier way to solve this and to simplify this would be to, the answer would be that same base, but I'm just going to subtract those two exponents, and that will give me the answer anytime I am dividing. So let's say this, let's say, and if you want to kind of think about it again, you know, if I have, just to, you know, write it out for you guys like I did with the product rule, is let's say we have, I don't know, let's say 6 to the 4th power, and I'm dividing it by 6 to the 2nd power, just to give you guys a simpler one here. Remember, exponents mean multiplication here, so this means 6 times 6 times 6 times 6, and then I'm dividing by 6 times 6. So, you know, what happens here when I've got the same number on the numerator and the denominator, technically what's happening is the same numbers can cancel out, and it leaves me with these two left over here on the top, which would just be 6 to the 2nd power. So you can see all we've done is we've taken these two exponents in our problem, and all I had to do was subtract those two. So 4 minus 2 gave us 2, and that's how we got 6 to the 2nd power. So even in simplifying problems when we're dealing with exponents, they show us in that example on that chart, or yeah, that chart on page 21, that t to the 6th power divided by t to the 2nd power, we would just simply take 6 minus 2 to get 4, so the answer here would be t to the 4th power. And that'll work every single time. And don't be thrown off when the number on top might be smaller. Because what happens if that first problem that I gave to you, let's say that was reversed. Let's say instead of 6 to the 4th divided by 6 to the 2nd, let's say instead we have 6 to the 2nd divided by 6 to the 4th. No need to be alarmed. Remember, what's going to happen here is, again, this represents 6 times 6, and down here this represents 6 times 6 times 6 times 6. So when we're canceling out those values, now what's left over is two numbers on the bottom. So that's just going to be represented as, my answer is just going to be 1 over 6 to the 2nd power. Another way to kind of think about this, and I did that because there's nothing on the top, so we'll just call it 1, and the two 6's ended up on the bottom, so there's 6 to the 2nd power down there on the denominator. But another way to think about that exact same problem, if I just get this part of the way, without having to draw out the factors like that, you won't have to do that every single time, but I want to show you, let me move all this here, that quotient rule will work because we're taking, again, we're subtracting our two exponents, and we know that 2 minus 4 is negative 2, thinking back to our integer rules there. So if we simplify this out as 6 to the negative 2, remember, think about what we talked about on the previous page, that whenever we have a negative exponent, I can simplify that by simply putting that underneath a 1, you know, putting it in fraction form, but then putting that base with a positive exponent down in the denominator. So we can see that that's how that would simplify. I drew that out a second ago in the factor form to show you that that's what's actually happening in these problems and why that quotient rule will work. So anytime you're dividing any exponent that, any base that happens to be the same with different exponents, remember you can simply just divide those two exponents to get that answer. Okay, now let's talk about, I want to go back to that product rule for a second, because I just thought about this and what you might see on your homework. Sometimes you may come across the product rule with different variables, with meaning different bases. And so what I mean by that is, what if we came across a problem like this? If I said maybe 2 v to the third times 6y times 4y to the sixth times v to the ninth. So something like this. Your product rule can still work here when we're simplifying this problem. Remember, what we can do is, like I mentioned before, when we were looking at just one variable, and I'll go back to this example. Remember, I showed you guys -5, I think it was 5w to the fourth times -w also to the fourth. Remember, what we could do is we combined our numbers, so -5 and -1, and that represented, -5 times -1 was 5, and then we just combined our the same base with our exponents there. W to the fourth times w to the fourth was w to the eighth. So we were able to do that. Now here in this above example, what we're doing there is we're seeing we've got different variables. What happens here is you can only combine like terms, meaning I cannot put v together with y. Only v and v will be able to go together, and y will be able to go together. But just like we did before, numbers are the same, so I can actually combine my numbers, 2, 6, 4, and then 1 in front of that v there. So we can separate those, and I'll put those down here, 2 times 6 times 4 times 1, and so there we're going to get our number answer of 2 times 6 is 12, times 4 is 48, times 1 is 48, so that would be our number answer. But now I can separate then our variables, but again we can only combine those like terms. So the variables there for v, I see v to the third, and then over here I see v to the ninth. So there's, I'm putting my v's together, v to the third and v to the ninth. And then over here looking now comparing, grabbing those y's, I have y to the 1 power, to the first power, and y to the 6th power. So I'm going to be able to combine those now. So v to the third times v to the ninth, remember what we can do is we can simply just add together their exponents. So that's going to give us v to the 12th power. And then over here I'm adding together the exponents for the y's, and that's going to give us y to the 7th power. And so our simplified answer would be this, 48v to the 12th, y to the 7th. And even if I had written down those v's first, when you go to solve this, I had mentioned this to you guys in class too, what you'll want is anytime you have variables then in your simplified answer, whichever one has the higher exponent goes first. So v went first because the exponent was 12, then y went second because the exponent was a little bit smaller. So that's why that went second. So just something else to keep in mind as you guys are working with that product rule, that remember you can only combine like terms, and that's something we'll talk about in another section in this chapter too. And that also applies for the quotient rule. So even if you're dividing by two terms that have different variables in them, you can only combine the same variables. You can only combine the like terms. So keep that in mind as you guys are working through your homework too, that the rule still applies as long as the base is the same. Okay, now the next rule, and actually the next three rules, I kind of like to think about the distributive property that we talked about last class, as it kind of works almost the same in that if you have any base raised to a particular power, for instance, this is the next rule down, and then you take that whole thing and you're raising it to a completely different power. An easier way to solve that, again, it's still multiplication, so this is kind of working the same way, that, you know, it's all, that's what exponents are, it's just a big multiplication problem. So that's why this works, you know, quickly and able to solve these. Whenever that's happening, you can simply just take that base, keep it the same, and then you can multiply these two exponents here. So n times m times n to get that answer. So looking at any exponent, say we have z raised to the power of 3, and I'm taking that whole thing and I'm raising that to another power of 4. So my answer here is going to be z still, but now I'm just going to multiply 3 times 4 to get 12, so my answer in the problem is going to be 12. So my completed answer would be z to the 12th. And so that's what's called the power rule, in that, anytime you're taking an exponent a base that's already been raised to an exponent and you're raising it to another exponent, that's how you get that answer. And then the same thing applies for even if you have a coefficient in front of your number. If you have 2y, let's say, I don't know, to the second, and you're multiplying that, not multiplying, but you're raising that to another power of, say, 4, the distributive property is kind of going to work here, in that you're distributing that fourth to the base 2. So think 2 raised to the power of 4 is what's happening here, and I'll simplify that here in just a second. And then you're distributing, so that was, there to see that a little bit better. And then again, to distribute it to the variable here, y to the power of 2, all I have to do is multiply those two exponents. So 2 times 4 is going to give me 8. So then it's going to be y to the 8th. And so I can simplify this a little bit further, because we know we can solve 2 to the 4th. 2 times 2 times 2 times 2 is going to give us 16. So our completed answer here is 16y to the 8th. So maybe an easier way to think about that is think about how you can distribute to each of the numbers inside the parentheses there when that is being raised to a certain power and raised again to another power. We simply just distribute that inside there. And really the same thing goes for the next one. And so this kind of goes with what I was just talking about. That was the example I just did, that if you've got a number in front of it, they show you in that the next row down, they're showing you a times b, and then if you take that and raise it to the m power, that's the same thing as a to the m and b to the m as well. And so that's what we just did when I showed you guys that example of 2y to the second times, not times, I keep doing that when I put the parentheses in there, raised to another power of 4. That's what we've done, is we've distributed it just the way that they did in that example. So they gave you even another example in that row there. They show you the same thing, that if I have 4 x, and then I'm raising that to the power of 3, that can be distributed as 4 to the third power and then x to the third power. And you can even further simplify that. 4 to the third power is 64, so the answer here would be 64x to the third. So just something to kind of think about there. And the same thing is going to apply for the last row down in that properties of exponents chart there, that it's showing you the same thing. If you have, let's say, a to the, or not even a to the anything power, I can show you an example with that. But a divided by b, if that is in parentheses and you're raising it to the power of m, that can be distributed in there. So even though your bases are not the same, that's okay, because outside the parentheses, that power is saying that it can be distributed to both inside the parentheses there. So that would be a to the m, then divided by b to the m power. So it shows you in the example that no matter what is, what it is that's inside the parentheses that you're dividing, they show you the example 2 divided by y, and if I'm taking that whole thing and raising it to the power of 2, well then I can distribute that 2 inside those parentheses there, and that would be 2 to the power of 2 divided by, distribute that to the y to the power of 2. So the completed answer here would be 4y to the power of 2 down there at the bottom. So just something to think about with those. I know we did some other examples in class and kind of putting some of these rules together, in that, say, I'm going to go grab some examples from the back and look at some of the ones that we did and how you can apply some of these rules. Like, for instance, I'm just going to grab number 45 from page 25, because that looks like kind of a complex problem, but I'm going to show you guys how we can put some of these rules together. It looks like we're going to apply the power rule on this one, and probably the quotient rule as well, but let's take a look. So we have, in number 45, we have 4x to the third times z to the negative 5. We're dividing by 12y to the negative second power. And that entire thing is being raised to the power of negative 3. Okay, so I'm sure this problem looks super complicated, but it's really not at all. Let me show you. So that negative 3, remember what we're going to do is we're going to distribute that inside the parentheses here. So I want to show you guys that one at a time. If we could just write out the factors and what's going to happen in this problem. So it's being distributed to each part of this. So even the coefficients there. So I'm just going to write this out as 4 to the negative third. Distribute that here, so that's going to be x, and then it was 3 times now negative 3. So I'm going to actually, just to save myself some room, we know that 3 times negative 3, positive 3 times negative 3 is going to be negative 9. So let's write that out. And then distributing that to the negative 5 in here, that's going to be z negative 5 times negative 3 is, again, same sign. That's going to end up being positive 15. Now down here at the bottom, distributing it to each part down here at the bottom, that's going to be 12 to the negative 3. And then y down there is negative 2. Negative 2 times negative 3 is positive 6. Okay, so here's what we have. We've distributed that negative 3, so we've been able to get rid of the parentheses. But now let me show you, we're also going to have to apply our negative exponent rule here. Remember, anytime we have a negative exponent, so for example, up here at the top, our 4 to the negative 3, for instance. So looking at that, remember we would simplify that as 1 over 4 to the third. Well, there's already all these numbers in here, so we obviously don't have to write that 1. But what's going to happen is that 4 to the negative 3, we're going to have to move that down to the denominator and make it positive. And then what's going to happen, since I already have a negative exponent down there in the denominator, I'm talking about that 12 to the negative 3 down there, what's going to happen is when there's a negative exponent in the denominator, that actually gets reversed. It's just like we're trading those because we don't want a negative exponent anywhere. So what happens whenever it's negative, we switch it. And so if it's already in the numerator, it goes down to the denominator. And when it's in the denominator, it switches to the numerator. So we're actually going to kind of trade these two numbers here. So our 12 to the negative third is going to become 12 to the third and go up to the top. And our 4 to the negative third will go down to the bottom. So again, we've switched that simply because their exponents are negative. The same thing is going to happen here with our x to the negative 9. It is also going to go down to the bottom as a positive exponent because it's negative. Now the other two, this z to the 15 and y to the 6th, since they're already positive, they're going to stay exactly where they are. So z to the 15 will stay on top here. Oh, let me write that out, same color. So z to the 15 will be on top, and then our y to the 6 will be on the bottom. And to simplify this even a little bit further, I'm going to go ahead and solve those numbers. Since 12, I already know that that's not a variable. I see 12 to the third down here, and 12 to the third, if I actually multiply that out, 12 times 12 times 12, or for those of you guys who have exponents on your calculators, you can take 12 to the third, and that's going to give you 1,728. And then I can actually go ahead and divide that by the coefficient at the bottom. 4 to the third is 64. So 1,728 divided by 64, if I went ahead and did that, that's positive 27. So what's going to happen is that positive 27 is positive, so it stays on top, but that's going to allow me to eliminate just those. It just becomes 27. So my completed answer here is going to be 27 z to the 15th over x to the 9th, y to the 6th. And that should be our answer. Let me double check because I've got the instructor book here, and that is the exact answer. So I know that seemed like a lot of steps, but keep in mind, again, you can only combine like exponents if there's, exponents that are the same in the numerator, denominator, and that power rule there just shows that we will distribute that to everything that's inside the parentheses and then apply our different rules from there. And so in that one we had to apply the negative exponent rule after we applied that power rule. So I don't know if you'll have anything that complex on next week's quiz, but that shows you when you come across those types of questions on your homework, keep that in mind that that's how we would just simply apply that. So there's a lot of practice problems there on page 25. Definitely take a look at those, and if you guys have any problems with those, let me know. But I'm going to move on to section 3, what we talked about on page 22. I think that was a little bit easier. I think you guys liked scientific notation. Scientific notation was really not too complex. It's used anytime we're trying to, it's just another way to represent a really large value, a really large number, even if it's something that's really big. So say if I have, 9,500,000, if I'm writing that, that's obviously a really big number, and that number can be used. We can write scientific notation for that as another way to represent that. But even a really small, large number, what I mean by that is something that's really small, but way less than 0. So even if I'm talking about like 0.00007, that's a kind of, again, a really small number, but scientific notation can be used to represent both of these. So what we'll do here is, again, scientific notation is simply represented as this. We write it out as A, so some number A, but A has to be between 1 and 10. So remember, that has to be between 1 and 10, or really I should say 1 and like 9.9, because it has to be less than 10. So like if we were writing out 1 million, we would use 1 instead of 10. So anything less than 10. And then we're going to write that out as times 10 to the nth power. And so that nth power is going to be dependent on how many times we have to move the decimal to get to A. So to show you what I mean by that, let's take, let me actually just erase what I just wrote down here. That A to the, you guys can see that there on page 22. But let's take that first example there, that 9,500,000. If I'm writing that out as, again, I want to convert that to some letter A, or some number A between 1 and 10. In this case, what I'm looking at is how many times I'm going to have to move this decimal. Again, in a whole number, we know there's an assumed decimal way down there at the end. How many times am I going to have to move that decimal to get it to something between 1 and 10? So if I move this decimal, let's say 1, 2, 3, 4, 5 times, that gives me 95. See what I mean by that? That 9 and the 5, that's where my decimal is. Still not between 1 and 10. So I move it one more time. If I get that 9 as 9.5, that is definitely between 1 and 10. So I've changed that to 9.5. So writing this in scientific notation, I'm going to write that as 9.5 times 10. And then again, how many times I move that decimal? 1, 2, 3, 4, 5, 6. I'm going to write that as times 10 to the 6th power. And like I said, that exponent is based on how many times you had to move your decimal. But in those numbers that are so large like that, the exponent's going to be, it's going to be positive. Whereas in that second value down there, where it's something that starts off as something really, really small, something smaller than 1, now I'm going to have to move my decimal to the right to figure out what that's going to be between 1 and 10. Moving that 1, 2, 3, 4 times is 0.7, still smaller than 1. Moving that now 5 times would give me the whole number 7. So writing this number out in scientific notation would be 7 times 10 to the 5th, because I moved it 5 times, but because I had to go the other direction, it's going to be negative 5. So that's how I would write that number in scientific notation. So kind of keep that in mind. If you're having to move your decimal to the left to make it smaller, that exponent's going to be positive. If you're moving your decimal to the right to make it larger, your exponent is going to be negative. And here's another reason why. Because let's pretend, oh, whoops, that's not my eraser. Let's pretend that we didn't do all that. Let's pretend that I don't know that, that this is my value up here. Let's pretend we don't know it's 0.0007. And I just gave you this number here in scientific notation. What this tells somebody who's reading this in scientific notation is that if I wanted to write it in standard form, that I am simply going to take 7 and there's the decimal behind 7, and I'm going to move it 5 times in the negative direction. That decimal, I'm going to move it 5 times in the negative direction, which, thinking about a number line, remember on a number line, here's 0, here are all my positive values, here are all my negative values. So when I say negative direction, I mean to the left. So the reader here is taking this decimal, moving it 5 times to the left, because that's the negative direction. 1, 2, 3, 4, 5. They understand that this is 0.00007, and that's exactly what it was. So that's why that exponent should be negative in that case. So anytime you have a value that's really, really, really large, and you want to write it in scientific notation, so say if I have, it doesn't even have to be super large. It can be something as large as just 12,000. Not a big deal. But I can write this in scientific notation by, again, taking this decimal, moving it 1, 2, 3, 4 times. I'm choosing 4 because I want it to be 1.2, not 12, because that's bigger than 10, and I don't want to go too far because 0.12 would be smaller than 1. And I need it to be between, again, 1 and 10. So I write this out as 1.2 times 10 to the, because I moved it 4 times, to the 4th power. Okay, so that's how I would write that number. And again, keep in mind that anything that's really small, so 0.003, would be written as, let's move this decimal 1, 2, 3, 4 times here. So I would write this as 3 times 10, but this time to the negative 4th because I had to move it to the right. So also keep that in mind. If I ever give you a number in scientific notation, then you should be able to then convert that back to standard form. What that means is, again, if I gave you, say, 8 times 10 to the 5th, that means in reading this, I'm going to take this number and I'm going to move that decimal that's behind that number 5 times, but in the positive direction, so I know that that's going to be to the right. So 1, 2, 3, 4, 5. That means there are this many zeros behind it, 5 zeros, so that makes this 800,000 in standard form because the decimal's now down here. So writing that out, don't forget, this is the number I'm looking for here. This, with all the squiggly lines under it, still has that decimal right here, so I don't want to see that as your answer. I need to see the completed answer without the decimal in that, or making sure the decimal's in the right place. So that would be 800,000. So if I then gave you, say, 0.00042, then moving this decimal, I'm going to move it to the right now. Oh, no, I'm sorry, guys. I told you guys I'm giving you all scientific notation now, not standard form. Scientific notation, but taking it back to standard form. I apologize. So if I gave you, say, 4.2 times 10 to the negative 3rd power, then again what that means is I'm going to take this number, so 4.2, and I'm going to move it this many times, but it looks like in the negative direction, so I'm going to take this decimal and move it 1, 2, 3 times, and that decimal now goes here. So because of that, my answer is 0.00, because I filled in these places right there with 0.42. So there's my completed answer, going from scientific notation to standard form. Okay, so that is scientific notation. Not too bad at all, just a decimal movement. The other thing that we talked about in class this week was we were looking at, we skipped over section R3, and now we are going to R4. I didn't worry too much about R3. That's something I don't think you guys will need. And we talked about polynomials. Polynomials just simply meant that we had multiple terms in a problem, and we were looking at what happens when we're adding and subtracting polynomials compared to when we're multiplying and dividing polynomials, which is kind of what we did when I was showing you guys the exponent rules and the, with the product rule and the quotient rule. That was multiplying and dividing, and we're multiplying and dividing with different variables. But when we're adding and subtracting, that was the thing we were looking at here on page 39. If you guys go to page 39 to see what I'm talking about there, we looked at how that's a little bit different. We can't apply the quotient rule here when we're adding and subtracting, because it's not really the same. And I want to show you guys, because I know that came up in class on Monday. If I have, say, w to the fourth power times w to the third power, remember that that simply meant w times w times w times w is that first one here, and then the second one here is w times w times w. And since this was a multiplication problem, and when we're multiplying these, again, it just became one long multiplication problem, so therefore we could just call it w to the seventh. Now that doesn't work when we're adding exponents, because it's an addition problem. If I had w to the third plus w to the second, now that's w times w times w plus w times w. So I can't just call this w to the fifth, because that's not the case here. Now that this is being added, it's not like it's one whole multiplication problem anymore as it was at the beginning. So I can't put these together the way that I could in multiplication. So what was happening when we're adding these, when we're adding and subtracting, and we're looking at, again, polynomials, don't forget there's that rule that we can only combine like terms. And in that case with w to the third and w to the second, these are no longer considered like terms because their exponents are different. I can't just put those together any longer. So they're no longer like terms. So when we have a problem, like I'm going to show you guys the one that's on page 39 to show you guys how they're doing that. I know they're writing that there for us, but I just want to walk through that and explain it as what they're doing. When I have a problem like that one that's in that example, where we have -4, and I'm just going to put it in parentheses because they're just separating the two polynomials for us, -4w to the third minus 5w to the second plus 6w plus 3. So there's one polynomial, and we're adding that to 8w squared minus 4w plus 2. Okay, so here's what we can do here. In this case, since we're adding these polynomials, we're not multiplying them. I can't separate the numbers anymore. The numbers, the coefficients that are on those variables are part of that variable. Again, because it's not a multiplication problem, so I can't just put them together like I could have before. Here we're adding them, or even if we're subtracting them, we would do the same thing. So I'm going to take what's considered our like terms, and that's, again, whichever ones have the same exponent on them. So looking at those, I'm going to look for the higher exponents first, as the higher exponents need to go first. So our highest exponent here is w to the third. So that is one like term. I do not see any other w to the third, so that's going to be off on its own. So there's -4w to the third. We've taken care of that one. The next highest would be w to the second. So I can look in this problem and I see there's a -5w to the second. We can even call it -5w to the second. And in this polynomial we have 8w to the second. So I'm going to write those down here, and just, our like terms are these two. And then it was plus 8w to the second. And it was plus because that's the operation we're working with right now. And then it looks like the next highest exponent is just w to the first power, so that's just called w. And I'm going to switch my color here to now yellow. And so we see 6w down here, and then I see a -4w down here. So I'll write that out then as plus, and it's plus because that's what's in front of that one, so plus 6w minus 4w. And then the last of the like terms are those that don't have a variable on it at all, so I put that in black here. That's going to be plus 3 plus 2. So then we have plus 3 and plus 2. That's a plus sign down here at the end. So now what's going to happen is we can go ahead and combine these like terms. Again, -4w to the third was by itself, so I'm going to go ahead and just write that one as I did before. And then I can go ahead and put these two together that are here in red. -5 plus 8, we know that is going to be positive 3, right? So I'm going to go ahead and put plus 3, and then that's a w to the second power there. So that those two just get combined when we're adding. those. And then I'm going to go ahead and put these together. I have positive 6 minus 4. We know 6 minus 4 is 2. So therefore the next problem here would be, or the next part of this problem would be plus 2w. And then lastly, I can go ahead and put these two together at the end. 3 plus 2 we know is 5. So the last part of this polynomial would be plus 5. So that's how we can solve that one. And we can't put any of these together now that they're no longer like terms. So when we're adding and subtracting polynomials, that's how we would put those together and how we would simplify that. So that would be our end answer. And you can see that that's exactly what they got here on page 39. Okay guys, so let's take a look at another one. I'm going to grab an example problem on page 44, back in the back of this section where it gives us some practice exercises. It says in the adding and subtracting polynomials, I'm going to grab just number 17 just because it's the first adding and subtracting polynomials question. So in that number 17 we have negative 8p to the 7th power minus 4p to the 4th power plus 2p minus 5. That's the first polynomial, and then we're going to add that to 2p to the 7th plus 6p to the 4th plus p to the 2nd. Okay, so now let's take a look and let's see what we can combine here that are like terms. So I can see here that we have 2p's to the 7th. I have negative 8p to the 7th and 2p to the 7th. So I'm going to go ahead and just write those guys down here. Negative 8p to the 7th plus, because we're adding, that's why it's plus 2p to the 7th. Okay, now let's see what else we can combine. It looks like I have 2p's to the 4th, so there's a negative 4p to the 4th, and here's a 6p to the 4th. So writing that down, that would be minus, because of the negative sign there, negative 4p to the 4th plus 6p to the 4th, and it's plus because that's what's in front of that one. Let's see, and then I don't have a p to the 3rd, but I do have a p to the 2nd, so that's this one right here, so I'm just going to add p to the 2nd. Whereas then I do have a p by itself, so that's this one right here, so I'm just going to put plus, oops, I'm sorry, it was plus 2p, and then I have one number by itself without any variable on it, so I'm just going to write that one out by itself. So those three down there at the end are going to be just on their own. They're going to be part of this simplified problem. Whereas the first two sets there in yellow and blue, I can go ahead and put those together. So I'm going to simplify my answer down here. Negative 8 plus 2 I know is negative 6, so that's first part's going to be negative 6p to the 7th. The next part, I'm putting together the negative 4 and the positive 6, so we know that that's positive 2, so that's going to be positive 2p to the 4th, and then since those last ones we cannot combine, I'm going to go ahead and just write the rest of that out. So that's going to be p to the 2nd plus 2p by itself minus 5. And I want to double check just looking at the answer that I have here in my instructor book, and it looks like that's the simplified answer. So I know that seems crazy that this is the simplified answer, but that's how we add those polynomials. Maybe later if somebody came in and told us what p was, we would be able to solve this equation or this expression here. But right now, when we have those variables with those exponents, we cannot combine those, so that is how we would do that. That's how we're going to add that polynomial. And now taking a look, just real quickly, looking at how we would multiply polynomials. We've kind of already had some exposure to that as we've done that a little bit in applying those exponent properties. But I'll show you guys, looking at some of the multiplication of polynomials down on the bottom of page 39. If you are multiplying a polynomial by, I'm looking at the second bullet point. I'll come back to that first bullet point when we talk about that in the next example. Everything, and really in all of these examples with multiplication of polynomials, you're just applying the distributive property is what it is you're distributing everything from the first polynomial to the second one, and so that's how you're going to combine those two, and you're able to again apply that exponent rule that we discussed earlier. So I'm looking at the second bullet point at the very bottom there of page 39 where it says negative 3x to the 3rd times 4x squared minus 2x plus 6. So again, you can distribute everything that's in that, and you can just distribute it to every part of that polynomial inside the parentheses there. So you can just, and they show you that we can just distribute, and they've kind of combined it and showed you multiplication problems here, that this would be negative 3x to the third times 4x to the second. Whereas then distributing the next part would, then we're going to just, let's see, then we'll end up adding just the second part to it, which is going to be then negative 3x to the third minus 2x, and it's or times negative 2x, because that's what we're doing, is we're multiplying. So what the next part is. And then let's see, then we're just going to add the last part together there, which is going to be negative 3x to the third times 6. So then when putting those together, we can see that first part, we can take, let's see, negative 3, there's this part right here, negative 3 times positive 4 is going to be negative 12, and that's going to be x to the 5th, because we're putting those together there. And then we're adding that to the next part that we've distributed. So negative 3 times negative 2 we know is positive 6. So the next part there is going to be plus 6. But it's going to be x to the 4th. Because we're, again, that's the adding together 3 and then 1, since that x doesn't have anything on it. So that's x to the 4th. And then we're going to add that next part, which is negative 3 times 6 we know is, oops, I went ahead and wrote that minus sign, and that is not going to be the case. It's going to be, that plus sign, and it's going to be minus, because negative 3 times 6 is actually negative 18, so we're going to write that as minus 18, and then there is no exponent on that 6, so we just call it x to the third, because we're just writing that one down. And that's how we would add, that's how we would multiply the polynomials, because now we have, once we've distributed each part into that polynomial, remember that each part there, we had these different operations taking place inside this polynomial. So again, I can't combine now what's at the end, because we're adding and subtracting these different parts of this polynomial now, so I can't just combine those bases with those exponents anymore. Now they're different terms, and we can't combine those like terms. So our solved answer down here would just be negative 12x to the 5th plus 6x to the 4th minus 18x to the 3rd, and that would be our completed answer. Now when you get down to multiplying two polynomials with 2 or more terms, which you can see at the very, very bottom of page 39, where it says the 4w plus 7. We ran short on time, so I didn't go over this, so I'm not going to put anything like that. I would probably just give you guys an example like the one we just did, where it's a monomial, because it's just one term multiplying, and that's easier to distribute. Although next week we'll talk a little bit about how we can do that bottom one, and how we would still apply that distributive property, because we can distribute from one polynomial to the next, and it's really not too bad, but I'll show you an easier way using what's called FOIL, which says we can apply the first and then we multiply the outside, and just to kind of show you what I mean, what I said in this, FOIL means we multiply the first, then the outside, then the inside, and then the last, and that's what FOIL stands for. So that's how we can quickly multiply polynomials that have more terms in it. But since we really didn't talk too much about FOIL and how we can do that, I won't put that on next week's quiz. So that's all. That's the only things that we discussed last week. So I hope that helps with those different things. And if you guys run into any questions on anything, you guys please don't hesitate to ask. I will be here. Thank you.